Hello everyone and welcome to my channel. Today I want to delve into one of the most important models in chemical engineering and gas-solid reactions. It means unreacted shrinking core model. This model has various applications in steel making, iron making, and environmental processes such as absorption of gas pollutant. This model helps us to predict and analyze the reaction behavior of this reaction system. As far as this model has not been thoroughly covered in the textbooks, I try to explain the theoretical and mathematics behind the unreacted shrinking core model in a simplified manner. So let's get started.
Alright, let's dive into the unreacted shrinking core model under the condition where the gas field is the controlling factor. We assume that we have a gas A, such as hydrogen or carbon monoxide, reacting with a solid B, like iron oxide or nickel oxide. So this reaction, gas A reacts with the solid B to produce gas C or solid D. So here you can see a figure which explains the unreacted shrinking core model. Here we have a pellet with a capital R comes into contact with a reducing gas, and after times using shrinking the radius of pellet B, we can calculate the solid conversion. We can assume for every mole of A, we need B mole of B. And then we can write a molar balance as DNA equal to D and B divided by the stoichiometric coefficients. Then by cross multiplying both sides, we have D and A multiplied by B equal to D and B. This is an important relationship, so I'm highlighting it in red. Next, we consider the flux of mass transfer. For the gas field, which I denote by Q. The flux represents the rate of reaction in relation to the surface area. So we can write it as -1 divided by external surface area multiplied by D N A over D T, which represents the changing mole of A by T over T. And now I want to open the external surface area, which is the 4 pi r squared. We can also express the flux in terms of mass transfer coefficients as Q equal to Kg multiplied by concentration of gas film minus the concentration of surface of pellet. When we talk about the concentration on surface area, we talk about this area. The green highlights show the concentration on gas field, and a surface on outside of a red circle it's explained the concentration of surface, uh, and it's a Herculean task, you know. In the chemical engineering problems, we often simplify the concentration on the surface. And in this model, we assume it 0 because obtaining the surface concentration is extremely difficult. If I were to give you an idea of how challenging it is, I would say that in 2007, Professor Ertel at Max Planck Institute won the Nobel Prize in Chemistry for using experimental techniques at nanoscale to determine the surface concentration for processes like Haber and automotive catalytic reactions. Now, with this simplification, we get minus 1 over 4p r squared multiplied by dNA divided by dt equal to kg CAF. Now to analyze the change in solid particle, we use the relationship we highlighted earlier and substitute dNA with dNB. So we can rewrite this as here. Now we can write minus D and B over 4 p r squared b and dt equal to kg multiplied by CAF. Now we need to know about how we can calculate the D and B to make a connection between the unreacted core and the molar of solid particle. So we know that NB can be expressed as a molar density rho B multiplied by volume of pellet VB. And besides that, we know the volume of solid B can express as 4 over 3 multiplied by P r squared, but it's a RC because it's explained about the radius of remained B. Pay attention that RC changes during the times. Since we have NB in differential form in the flux equations, we need to do differential form of that. So we write dNB is equal to rho B multiplied by 4 p r squared or c squared multiplied by d or c. We highlight it as equation 2 and use it here. Now, by this substitution, we have minus rho b multiplied by 4p over 4p r squared multiplied by b multiplied by the integral of rc squared drc is equal to, by multiplying the dt with kgcaf, we can write dt in integral of 0 to t, and here capital R to RC. Now we bring these two terms into denominator. Now we can cancel out the 4p terms to arrive at the new relationship. And now we can integrate the both sides. So we can write minus rho b over r squared b kg caf rc cubed over 3 minus capital R cubed over 3, and now, sorry, on the other hand side we can write t. Now, by factoring r cubed over 3 out of parentheses, we can write rho b over b kg caf, and here we have r cubed over 3 r squared multiplied by 1 minus rc over capital R cubed. Which is equal to t. Now r cubed is simplified with r squared on both sides of fraction, leaving just r in numerator. So we can now write the final equation, which is t is equal to rho b r over b kg caf 3 multiplied by a parenthesis, which is 1 minus RC over capital R cubed. Ultimately, this gives us a function to calculate the time required for reaction to each different radii. Now, let's look at how to determine the solid conversion, it means xp. The term 1 minus xp represents the ratio of volume of unreacted solid to the total volume of solid. So we can write 4 over 3 p RC cubed over 4 over 3 p capital R cubed. This leads us back to the same equation we derived, as xp is equal to 1 minus RC capital R cubed. And there is also a final time which happens in when RC is equal to 0. This can be called the final time and represents with tau, which is equal to rho B R over B kg CAF 3. If we consider T over tau, we arrive at the final relationship. If you refer to Levenspiel book, you will find this equation which we have now derived. In this video, we covered how to determine the solid conversion and reaction time in the spherical case under gas film control. In the future videos, we will explore the scenarios where diffusion and chemical reaction are the controlling factor. Thank you for staying with me this far. If you have any question, feel free to ask.